Welcome back to Zero Dark Emissions. Last time we left off with the installation of the actuators, and in this episode we will be wrapping up the final pieces of the primary EV systems and performing functional testing. This will include further testing of the BMS, now powered by the 12-volt battery, along with the onboard charger, ensuring that we can charge the high-voltage battery pack from the wall charger, the DC-to-DC converter, ensuring that the 12-volt battery is being charged off of the high-voltage pack, and the inverters and motors, ensuring that the motors perform based on our driver inputs through the inverter. Before connecting the BMS and onboard charger to permanent power for testing, I'm first going to temporarily connect the display, since this is part of the CAN bus, and we will need the CAN bus to be completed in order to ensure that the other items that we are testing on the CAN bus have this completed network. This is particularly important for the display, since the display is at one physical end of our CAN bus and contains the 120 ohm termination resistor within the unit for this end of the bus. Next up here, you can see we have made the final high voltage connections at the battery box. The first is the negative connection here in the secondary battery box, and this is the positive at the rear of the main battery box. This connection is temporary since it will need to feed through the doghouse on the battery box cover, so we will need to remove and reconnect after the cover goes on. This line can now be plugged in at the control box side. The next thing that we will handle is temporarily connecting the main 12-volt power and ground from the control box to the main panel. This is circuit X107A here, which provides constant power to the BMS and SIM charge. I also previously thought that 12-volt power was needed for the onboard charger here, but this is actually an optional 12-volt output, so I removed the line and pin from the intermediate connector for this. Here we have Y401A, the main ground of the control box, which then provides ground, really 12-volt negative, to the BMS, SIM charge, OBC, and J1772. We have also connected the main 12-volt lines from the 12-volt battery to the panel and are now ready to test the BMS and charger. So with these needed connections made, we will now test the charger, and this was unsuccessful. After much discussion with Vero, the BMS manufacturer, we determined that I had the pins reversed on the SIM charge plug, and this was due to the fact that I actually do not have the SIM charge, but rather a similar unit called EVS CPI, which was a replacement for the SIM charge. It appears that I ordered this unit right as the transition was being made, so I had the install manual for the SIM charge even though I have the EVS CPI. Alright, so at this point I've changed out the pins on the connector for the EVS CPI, which is here, and I plugged that back in, and I'm definitely getting better results, but still not quite right. And you'll see here this says ready currently, but when I plug in the charger, you're going to see that it does go to charge, and you'll see the wall charger is going to start blinking blue, which means that it's charging. But you'll notice here that this input 4 is not showing up, which is the control pilot input, meaning that my wall charger and the BMS are not talking to each other. So something's still wrong. After talking with Vero, I think probably what happened was when this connector was reversed, I probably cooked something in here. So I got to get a new one of these, except that they don't make this anymore. It's now the Vero Charge. And so this also will have a totally different connector. It's actually 10 pins instead of 8. So I've ordered that. Once I get that, I will then again switch out all those pins into the new connector, plug in the Vero Charge, and then hopefully that will do it. One thing you'll also notice here is I did plug in the display for this is the BMS display. I'm not using that. That's the thing that I added as a possible, something I could add in, but it is working. That's good, but I'm not using that anyway. That's going to go to our main display. So anyway, once I get the Vero Charge, I'll rewire that, plug that in, and hopefully that'll do it for us. So at this point I have the new Vero charge unit installed, but I am still not getting a successful charge. You can see here that it does go from ready to charge and input 4 is lighting up, meaning that the Vero charge is telling the BMS to allow charge, but there is still no current flowing to the batteries. After some discussion with Vero and after testing the CAN bus, I found that I am getting 0 ohms across CAN high and CAN low, which means that I have a short in the CAN bus. I should be seeing 60 ohms between CAN high and CAN low. So I need to do some more testing of the CAN bus to narrow down the problem and correct where needed. In the meantime, I'm going to temporarily just connect the CAN bus only to the BMS and charger, along with a temporary 120 ohm resistor at the BMS end, in order to simplify things for now. Okay, so I built a temporary CAN bus between the BMS and charger only, along with the temporary 120 ohm resistor here, and I do have my 60 ohms across CAN low and CAN high. However, I'm still getting the same result. After more discussion with Vero, I have purchased a device that can plug into my CAN bus, and along with its associated software called PCAN, it provides me with the CAN messaging that is occurring while I have the charger plugged in. This plugs into a serial port, and here you can see the serial port that I have temporarily wired in. I will also be wiring in a permanent serial port in my permanent CAN bus so that I will be able to plug into the CAN bus at any point in the future as needed. Here you can see the CAN messaging provided via the device and associated software, and everything appears to be showing properly. The first 9 lines are messages coming from the BMS, and according to Vero, these are all reading properly. The last item is the message coming from the charger, and this also appears to be okay. So the next thought is that I may have a hardware failure with the onboard charger. I changed out the charger with a new charger, and still not working. The next thought is that perhaps I have an issue with my wall charger. This is a brand new wall charger that was purchased and installed for this vehicle and has never been used before, so that is a valid question mark. I went ahead and purchased a 120 volt charger, which is useful to have anyway, in order to see if this would provide charging. I plugged this into the vehicle and also changed the BMS settings for a 120 volt charger, and same result. As with the level 2 charger, you can see that the wall charger display appears to be normal, showing that the charger is in a charging state with the blinking green light, but same results. So more discussion with Vero, as well as the charger supplier, and Vero sent me one of their demo BMSs to plug in order to see if I have a bad BMS. I plugged that in expecting to either see it working, meaning that my BMS was bad, or providing the same result, meaning that my BMS was okay and the problem was elsewhere. However, that was giving me a worse result than my BMS, so it looked like the demo BMS was actually bad. Vero was getting ready to send me another demo BMS, but the charger supplier had mentioned that it may be an issue with the AC power getting to the charger, and although I was pretty sure that power was flowing to the charger connector, it occurred to me that there might be a problem with the connector itself. The AC plug that I was using was the one supplied with the original charger, which I had to wire myself. The new charger came with a new plug that was pre-wired, and when I compared the two, I noticed that the contacts on my plug were not visible at the end of the plug like they were for the pre-wired one. So I think we're onto something there. You can see here that I've got the new plug wired in and we're ready to try again. Okay, so I've got the new plug in. I'm gonna go ahead and plug the charger in now. You can hear the click for the charger going on. You can hear the fan going on for the onboard charger. And I'm getting a good charge now, so success. Originally, I was not getting any current flow here. It was showing 0 even though it was charging. So I had to modify some settings there, and you can see it's good now. I also, for a time, was seeing is only 1.5 amps. So there's another setting I had to change. Now I'm getting what's the correct value, about 15 amps. So all good, I'm getting a good charge. So now we can ensure that we will not deplete the pack when we get to further testing, which is great. But before we go on to the next item, which will be the DC to DC converter, we need to get the full CAN bus back together and see if we can get the charging to work with the full CAN bus. Here you can see the CAN bus lines for the full CAN network reinstalled, along with the added stub with serial ports to allow future CAN message monitoring. And I've also got the Vero charge permanently installed in the box, as well as the box receptacles and plug for the charger and DC to DC converter that I temporarily removed for the temp CAN bus. And I am successfully charging as before with the temporary CAN lines. So now moving on to the DC to DC converter, and I have already connected the 12 volt lines between the DC to DC converter and the 12 volt battery. Here is a look at the CAN messaging output while I am charging. As before, the first 9 messages are from the BMS, all normal, and the last 2 messages are for the charger, also normal. And now with the full CAN bus installed, and with the DC to DC connected, we also have an additional ID tucked in between those 2 groups for the DC to DC converter. However, we should be seeing a second CAN ID when the DC to DC is charging the 12 volt battery, so we have a problem. After discussing further with Vero, they sent me updated firmware to flash to my BMS that commands the DC to DC charger to operate when I am in the drive or charge states. They can provide custom firmware that would command the DC to DC to work in any of the BMS states, such as drive only, for example, and I will probably want to expand this in the future to command the DC to DC in any state except error, basically to always keep the 12 volt battery topped off. But for now I like the limited states of drive and charge only, which is pretty close to always, but will limit it to when I am around the vehicle to monitor what is happening. Okay, so I've got the DC to DC connector connected to the battery, both the positive and the negative. So now with that connected and the new software, the BMS software updated, you can now see in the CAN view that we're getting 2 IDs that are related to the DC to DC. So that's great. That means they're communicating, and that won't start charging until I'm into charge mode. So I'm going to put it into charge. Plugging in. Now you can see the 2 CAN IDs show up for the charger as that engages and starts charging. And this is also now sending charge to my 12 volt battery. Basically these CAN IDs, this 01 means that it's working, starting, and then this is giving information on voltage and current, temperature, whatever. So we're good. We will next be testing the inverters and motors, and in order to do that, we need to make some additional temporary connections, including the connection of the EV harness to the main panel and to the starter switch, and some other temporary connections for powering up the inverter only. With these temporary connections made, we can now attempt to program each of the inverters through the serial ports that we installed previously. The first step involves using software called C2prog, which installs the latest firmware onto the inverter. This requires that we ground one of the pins at the inverter connection, and we are handling this via this switch that we installed in conjunction with the serial port, which was covered in episode 15. This switch will eventually light up when depressed when fully connected later. Now here you can see that we have a good connection with the inverter, a good first sign, and we can now attempt to install the firmware, which is a hex file with a file name that includes the date of the release. And here you can see that the C2prog software successfully installed our firmware. We can now cycle the 12 volt power to the inverter and also unground the program enable via our button. The next thing is to connect to the inverter with a program called RMS GUI, which is what allows us to see all of the parameters called EEPROM that the inverter is using to control the motors, and also allows us to modify those parameters as needed. The RMS GUI references a text file called defsims, and the defsims file has a matching date code in the file name as the firmware file, and the RMS GUI is showing the firmware version that we just installed. Here I am reviewing all of the EEPROM parameters for our test condition. I first attempted to test the motors by sending a CAN command rather than installing all the inputs for the accelerator, brakes, and shifter functions. However, that did not work very well, so I'll be doing this via these actual inputs. In order to test, we need to temporarily connect the cooling system. I don't think that we'll be running the motors long or hard enough for cooling to be needed for the motors. However, the inverters require cooling for any operation, even if for a brief time, in order to prevent damage. I'll show the full cooling system installation in a future video. So after changing some of the EEPROM parameters for my setup, we can now attempt a test of the rear motor. I had some false starts with some bad wiring connections and EEPROM tweaks, But after resolving those basic issues, I had a partial success, but not quite there. At this point, I have the rear motor spinning, which is a really positive sign since it rules out a number of possible bad connections, and these are working in both forward and reverse. But I have a condition where the motor stops after briefly running. The inverter is showing that it is going back into state 4, which is the wait state, and then back again to 06 motor running state, and the BMS is showing an error state along with the series fault, so I need to figure out what's going on there. At first I thought I had a possible issue with EMF coming off of the 3-phase high voltage lines, which are located somewhere close to the BMS, and I actually had my laptop zap out when I had it located on top of these lines. But after temporarily providing more separation between the BMS and the lines, I had the same issue. Also, the bouncing between states is happening even when the high voltage power is not applied to the motor. So after some discussion with the motor and inverter manufacturer, I learned that I was improperly grounding the driver inputs from the inverter. The accelerator is an analog signal. This has a variable input of 0 to 5 volts, which determines the motor speed, and the forward, reverse, and brakes are a digital signal, just a 0 or 1 for on or off. The inverter has dedicated analog and digital ground pins, which are to be used to ground these items as opposed to the overall system ground that I was using. So after modifying these for A ground and D ground connections, I tested again, and same result. At this point, I decided to test the front motor independently just to make sure that the front motor was basically working without any additional issues from the rear, and after adjusting the EEPROM values as with the rear, I had the same partial success that I had with the rear. That is to say that the front motor is spinning but has the same EMF cutout issues that I have with the rear. So with this partial success, I'm now going to change the setup to utilize slave mode for the front and see if I can get that working. Slave mode basically allows me to have the rear inverter act as the master and have the front controlled by the rear inverter over CAN rather than through the VSM inputs. This allows the front to have the same commanded torque as the rear so that they stay in sync. So after a couple of minor false starts, I was able to determine the correct EEPROM changes at the front and rear inverters to get this working. So this is a big success. You can see the front motor spinning here, which I have disconnected for now so as not to spin the wheels. At this point I received updated BMS firmware from Vero that adds a custom timeout delay for the battery modules so that I can increase the delay for when the BMS goes into error state if it does not receive good information from the batteries. The thinking is that perhaps if this timeout is delayed, I will get a signal from the batteries over this longer period of time. So after uploading this firmware to the BMS and increasing this delay from 5 seconds to 40 seconds, it worked. With the 40-second delay, the motors continue to work even beyond this 40 seconds, meaning that the BMS is getting a good signal from the batteries within this timeout range. Since we want this delay to be as short as possible, I attempted to test this down to a lower delay for the shortest possible delay that still works, but 40 seconds was the shortest time frame that was reliable. So this is a huge milestone, and we now know that the motors are fully operational, minus some fine-tuning that we may want to make later on. The last thing here will be the installation of the battery box covers. This requires that we disconnect the high voltage positive line at the rear, and then we can reconnect it after the cover goes on. I'm also removing all of the temporary body wiring harness connections and draining the coolant and partially removing the coolant lines to get all of this out of the way for not only the battery box cover installation, but also for the upcoming body installation. Since the secondary box can be installed after the body goes on, I'm going to leave this off for now, since I have better access to the inside of this box without the top on versus the more limited ports, just in case any future adjustments are needed. Notice that before placing the main battery box cover, I'm also epoxying the connection bolt to the bus bar, since I won't have good access to the bolt head with a wrench from the access port only once the main cover goes on. So this lets me tighten the line connection from the top only. I'm also installing the brake line to the rear at the driver's side of the box. As well as the vent line and cable for the antenna at the passenger side of the box now, since the clips for these lines use the battery box bolts. Finally, we will place the access covers. Here you can see the breather valve installed on the access cover, which lets the pressure equalize inside the box based on temperature fluctuations of the batteries. So the completion of this basic functional testing is a really huge milestone and essentially completes the main EV portion of the build, although we do still have some subsystems like the cooling, steering, braking, and the display, as well as fine-tuning some of the EEPROM parameters with the motors later on. At this point, I want to give huge props to Vero Electric, particularly Rita at Vero, who provided an enormous amount of support and was really patient with my novice questions. I really love their BMS, but the support that came with it was outstanding. If you're using Tesla batteries for an EV build or for power storage, you should definitely give their BMS a good look. Okay, so with this big milestone behind us, I'm now going to move on to the body, which I'm really anxious to handle, starting with some body modifications that need to be made. So we'll take that in the next episode. See you next time.